Perfect. So I am Kunal. I'm a former lab member of these. We we were together. I think we had an over year's overlap. I don't know. It was COVID time, so everything is kind of blurry. But I graduated from Michigan in 2021, and now I'm a postdoc at MIT working with Professor Chuchi Fan. And today I'm going to be talking about some of the things that I've been working for last 1 year. It's a mixture of something that I did during my last postdoc at Santa Cruz and some of the more recent things that I've been doing here at MIT. And as I said earlier, some of these things are still under progress. So, I mean, we are still waiting on obtaining better results, but I'll still present some of the ideas that we have been working on and see and you can see if these are useful for you, and um, let's have some discussion about it towards the end. And if you have any questions towards even during the presentation, just feel free to ask them. Don't wait for the end. All right, let's see. So I'll start with some motivation about why do we care about safety and connect in general safety of autonomous systems, and particularly when we have attacks and fault, and why does it become even more complicated and difficult. So everyone, I guess, would be aware of different kind of what we call as CPS, cyber physical systems that surround us, particularly in today's era of autonomous connected system, where we have been talking about capabilities where the cars can communicate with each other for coordination. I mean, they're obviously connected with internet and their base systems for getting data and doing their computation, which makes it essentially a connected system, or in general, a cyber physical system where we have a cyber component of things being connected to each other or to the internet or to sensors or to satellites, and physical component being the car itself. There are other examples of cyber physical systems as well, where, for example, we have this energy distributing system, the grid, power grid, which is again a huge CPS or cyber physical system. And then at an abstract level, we can imagine a multi-agent cyber physical system where the agents are connected to each other, communicating with each other for coordination, connected to satellites like GPS or internet satellites or local network system for better communication and getting instructions from the base and whatnot, right? So that is essentially what we think about when we talk about a connected system or a cyber physical system. Now, why do we care about safety of the cyber physical system in particular? Well, because of the presence of the cyber aspect, the connections to internet and to the ground station, these CPS are particularly vulnerable to cyber attacks, right? And there have been a lot of successful cyber attacks in the past few years. Now these are some old news, Stuxnet and Triton malware attack or other kind of attacks that have been launched successfully in different parts of worlds. But it is still a very big problem as to how do we ensure that our systems are in some sense robust or resilient to these cyber attacks. And one of the arguments that everyone working in the field of cybersecurity give is that we can use some sort of encryption or other technology to make system resilient to cyber attacks, in the sense that you are unable to launch a cyber attack on the system. But then a lot of work has been done and a lot of literature argues that it is almost impossible to guarantee that your system will be attack proof at all in all possible scenarios. So it is essentially impossible to make the system secure that no cyber attack can be launched against it. So I think more focus has to be done on how do we make sure that even under these kind of attacks, the system does not fail in some particular sense, or at least we can maintain some sort of safety properties. And then we'll talk about what we mean by these safety properties in the next few slides. But in general, these attacks can lead to different kind of failures, and particularly we might run into big scale failures with a lot of loss of money, and in some cases, human life as well. And so we really want to take into account these considerations while designing the system itself so that it's resilient to certain classes of attacks, and that these properties of safety, which basically would save us money and human life and other things would are always guaranteed. So one of the things that is crucial here is fast and effective response. We do not want our system to detect that there is a fault or that there is an attack after, let's say, days of attack, right? The system has to be very quick in detecting that there's something wrong, and then it has to respond also very quickly and effectively, in the sense that it should respond in a way that it is able to recover from these attacks successfully. And for that, what we need is some sort of provable guarantees that even under these attacks, we are guaranteed that our system would not fail. Again, not everything can be guaranteed, but certain properties, certain safety properties can be guaranteed, and that's something that we are going to talk about. And particularly, this is more important for safety critical missions. So very simple example could be your drone flying in an enemy zone, and the least you want is that even if there is a cyber attack launched on the drone and it gets if the enemy is able to remotely access your drone, even in the worst case possible scenario, your drone should not crash back to your ground station, or in general, it should not crash on the ground. If you are able to recover it safely somehow, that would be the best case scenario, right? But at least it should not crash back on your ground station itself, destroying your whole equipment and possibly harming the human present there. So these kind of safety critical missions mean more we need to work more towards providing certain guarantees so that we do not have failures in these kind of missions. The issues with some of the prior work is that either there are no formal guarantees, particularly on safety. Most of the work focuses on performance issues, such as, the system would still maintain stability properties, it would not deviate too much from its nominal trajectory or its goal point or whatnot, but they do not consider safety as a big issue for whatever reason. And even in the papers where safety is considered, very strong assumptions are made about either known fault scenarios or how much system, about the tolerance of the system itself. Some of the more recent work about fault or cyber attacks basically assumes that you have redundancy either in your sensors or actuators, so that even if, let's say, you get attacks on your GPS, and let's say your GPS gets spoofed or your communication links get broken or attacked, you still have redundant connections to be able to sustain that attack and recover safely. But that's not a realistic assumption for smaller drones or cheaper equipment, and that basically induces huge cost burden over the design of these physical systems. And so what we would desire is to make guarantees without having these strong assumptions. Particularly, we don't want any redundancy assumptions. We have one sensor, if this fails, what can we do about the system? And if we have one actuator, if that fails, what can we do about the system? Right. So that's, go ahead.
Sorry, quick question. I'm sure you're gonna get into it, but like, I want to see where the distinction between like hacking versus like cyber attacks is. When you say cyber attacks, do you mean like they can change the code that's running on your system, or do you assume like they can send you signals that you weren't expecting?
That's a good question. So there are different attack models, and what we consider, and I'm going to only present one particular scenario here, but essentially we consider two kind of faults or attacks in the system. One is attacks on the system sensors. So the sensor values can be manipulated arbitrarily. So again, going back to that example of GPS spoofing, your GPS gets spoofed, you don't get any signal. But then you might also have a man in the middle kind of an attack where you get some manipulated data, some wrong data, or some gibberish data, right? So that's possible. Same goes for actuator signal attacks. So you might be able to access the communication line from your microcontroller to your actual end effector and either block it completely or give some arbitrary signals into it so that your actuator behaves completely erratically, or you can try to control it in a worst case possible, depending upon what your objectives are and what data you have available about that particular system, right? So these are the scenarios that we consider, basically just manipulating the end effectors in terms of either sensors or actuators.
So in some sense, it's like the input output could be affected, but the core logic of your controller is still sound. Is the
yes,
cool.
yes.
That's fair.
We are not considering, right. All right, any other questions? All right, great. Moving on. The fault model that we consider, or the attack model, I mean, I'm going to use fault and attack interchangeably. The first half of my talk would be about attacks as such, and the second half would be particularly entailed towards faults. But I mean, I'm sorry if this is confusing. I took the first half of my slides from one paper and the second half of the slides from another paper, so the terminologies might not be consistent. But essentially, the model that we consider for faults or attack is as follows. So we start with a general nonlinear dynamical system, and we consider this. We consider this division of inputs that are for the system. And in this particular work, in today's talk, I'm going to focus on attacks on system input. So essentially, the idea is that, let's say you have 4 inputs to your system, and one of them is vulnerable. You can get attacks on that one particular input, or your input might be faulty. And the simplest example would be a quad rotor where one of the motors is faulty, or the cyber attack is launched on the signal of one particular motor. So that's the division here. We have some vulnerable inputs, some secure inputs, where we assume that these inputs cannot be attacked. These inputs cannot be modified from what was assigned by the user, and these vulnerable inputs can be manipulated in arbitrary stance as long as this the assigned signal is still in the compact set of allowable signals, right? I mean, even if we assign an arbitrary signal, the actuator itself would have some sort of saturation because of its physical limits. So we still consider that, but other than that, the signal could be anything. And again, just a simple example would be either a faulty actuator in a quad rotor in terms of the propeller itself or the motor being faulty, or you get an attack from an extraneous entity on one of the communication signals to the motor. And what can it lead to is essentially either loss of partial or full actuation in the control surface, and that would lead to certain issues in the normal behavior of the quad rotor. And we want to make sure that at the least the quad rotor should not crash on the ground. It might not be able to track its desirable trajectory. It might not reach its goal point in the given time or as smoothly as we want, but the least we want is that it should not crash. It should not collide with the obstacles. It should not crash on the walls or on the ground or on the ceiling or wherever the safety boundaries are, right? So yeah, I mean, we can have fault or cyber attacks on these input signals. So more formally, the problem statement that we consider is along the lines of what I described in the previous slide, that given this system, given a safe set S, which is going to determine where our system should remain at all times, and given the attack model, again, that was described on the previous slide, dividing the input into this particular partitioning, what we want to design is first an attack detection mechanism. Right, so we should be able to detect that something is going wrong with the nominal operation of the system. and then a safe input assignment policy such that if our system starts in a particular subset of the safe set, resulting closed loop trajectories should remain in that safe set at all times, even under those attacks or faults. So we do not want our system to leave the safe set at any given time. Right. So let's see how do we deal with this problem of guaranteeing safety under cyber attacks or faults. So I know a lot of people in our audience would have a good background of for control value functions, but I'm going to just give a very, very brief overview just in case some of you are not familiar with what control value functions are. So consider this general nonlinear dynamical system and assume that the safe set that is given to us is just a zero sublevel set of a function B, right? So it's basically, let's say, it's a closed compact set which is defined by some function B. And we say that for this set S, this function B is a control value function if such an inequality holds at each point on the boundary of the safe set, which basically means that if you're on the boundary of the safe set, you are able to find a control input such that your system trajectories do not leave the safe set. And the implication of existence of a barrier function or control barrier function is that you can design a control policy for the system such that if you start in this set, your system trajectories would remain in this set at all times. And this is what we call as forward invariance of the set. And that's what we need. I mean, if the safe set is essentially everywhere above the ground floor or away from the walls or below the ceiling, if that's our safe set, then essentially we want our system to remain in that safe set and do not collide with the not collide with the walls or crash onto the ground and whatnot, right? So this is how we can formulate the safety requirement using this notion of control barrier functions. Right. So then how do we ascertain that the system might remain safe under attacks? So again, we go back to this model that we consider the fault model or the attack model. And then we consider this function, which is basically the modification of the function that I showed on the previous slide. And what we are doing here is we're just saying that even under the worst case possible signal that can go into the system, system should still remain safe. So whenever we are on the boundary of the safe set, even under worst case possible signals that can be injected into the system, this function H should always remain a non-positive, and that would guarantee safety. For some reason, I had some nice figures here. I don't know where they went. I might have changed the slide. I think it would have been easier to visualize what these conditions mean with those figures, but I apologize for that. But essentially, at the end of the day, what we want is to keep this function H non-positive at each point on the boundary, and that would mean that B is also non-increasing on the boundary, and so it would never become positive, and so we would never leave the safe set, which is defined as B being negative or non-positive. So that's the broad idea. All right, so what's an overview of approach that we take here? It's essentially very simple. First, we design a nominal feedback wherein there is no attack. We have a barrier function. We can assign a nominal input for the system to remain in the safe set. Then we use a different policy when there's an attack where we do not design the vulnerable inputs, because I mean, even if we design them, the system is not going to use them. So we assume that we do not have those inputs and they are actually acting adversarially. And we only design the safe or the secure inputs. And we are going to use them when the system is under attack. Now, the more difficult portion of this approach is to detect that there is an attack, right? And based on that detection mechanism, we are going to switch from this nominal input to this safe input or the secure input, right? And that's going to be the tricky part as to how do we detect that there is something wrong with the system. Now, one way to detect that there's something wrong is by using the barrier function itself. We can use the barrier function or its derivative to evaluate if the system is performing as per its nominal conditions. Oops. Oh, I pressed end and somehow we reached to the last slide. All right. I'll just quickly go to that slide here. All right. Yeah. So one of the issues in the approach that I described, where we can use the derivative of the barrier function to detect whether there is an attack or not, is that we cannot evaluate the derivative of the barrier function, right? And the issue is we do not know what input is to the system. We are designing a particular input, we are assigning a particular input, but that input is not going into the system, right? I mean, if there is an attack or there is a fault, this U signal is getting modified and we do not have access to the actual U that's going into the system. And so it's not possible to evaluate B dot exactly, particularly when there is an attack or there's a fault in the system, right? So then what we can do is we can just use a first order approximation, right? I mean, we can assume certain smoothness properties of the system dynamics and system trajectories and the barrier function itself. And then we can say that, oh, using the first order approximation, which is just taking the difference of the conjugative values of the function itself, we can find an approximate value of this derivative within certain error bounds, right? And then we can use this nominal condition to say whether there's something wrong with the system or not. Particularly, if everything is normal, then our derivative would be negative because of the presence of a nominal controller. We can assume that under nominal conditions, we can keep the system safe. And so our B dot should be negative. And so if this condition is satisfied, then we can say that, oh, system is working fine. There is no issue with the system. But if this is rather positive, or we can use a margin function, and I don't want to go into the details of how do we choose that, but the idea is that if this this particular quantity is greater than 0 or greater than this particular expression here, then we can safely say that something is going wrong with the system, and then we can flag that there is an attack. Now, there might not be an attack when this condition holds, but at least we would flag that system is very close to violating the safety constraint, and then we should act upon it and we should do something about it, right? And let's see how this particular algorithm works in practice. So for that, I'm going to present a very small simulation example for the quadrotor. Again, so as I talked about it very early on in my slides, for the case of a quadrotor, we might have a scenario where one of the motors is faulty or might be under attack. So here we consider the full 6 degree of freedom dynamics of the quadrotor, and we assume without loss of generality that motor number 4 is attacked. So we do not have control over motor number 4, and basically that affects all possible inputs to the system. And the objective considered here was very simple, just keeping the quadrotor hovering at an altitude of 5 meters. And the safety objective is that it should not crash on the ground. The least that we want is that it should remain in air even under these attacks or faults. And this video basically shows what happens to the quadrotor, and this is the attack and detection activity. So we basically launch periodic attacks on the system where the signals are pretty random on this particular motor number 4, and you can see that we are able to detect some of those attacks. There are some false negatives, there are some false positives, but the end result is that the system never crashes on the ground. Anytime it deviates from its nominal trajectory as dictated by the derivative condition of the barrier function, if we basically kind of like go into what you can call as a fail-safe mode, and then we just stop using this 4th motor, and then we design the other 3 motors to keep the system safe in the sense that it should not crash on the ground. And then this plot shows that the attack signals that we used without the detection mechanism would have been able to crash the quadrotor, but using this detection mechanism, they are able to recover it and kind of able to keep the system hovering at this altitude of 5 meters. So that's essentially what we are able to achieve. Yes, go ahead.
Kunal, is it also figuring out which motor is being, I know you said without loss of generality, you can assume motor 4 is the one that got damaged.
Yeah.
But is your detection also detecting which of the 4 motors is?
So this particular mechanism doesn't do it. So right now, this mechanism assumes that we know which actuator is faulty, right? And then we can just detect that something is going wrong with the system, and then we just because we assume that that particular actuator is faulty, we take actions with respect to this particular knowledge. So that is something that we are doing here. But basically, that brings me to the next part of the presentation, where we want to do a more realistic fault detection identification. So the issue with this control barrier function based fault detection was that, first of all, it assumes that we have a control barrier function. We have the function B that we evaluate and we use for detecting the fault, and we assume which actuator is faulty, right? So we do not want to make these assumptions. I mean, realistically speaking, we might not have this knowledge, right? I mean, any of the motors can get faulty at any given time, and any of the motors can get attacked at any given time. So this is something that we want to rely. Now, some of the prior work on fault detection and identification essentially uses this, what is called as residual information. So the idea is that, I mean, you have the actual output of the system, which you can imagine as just the system state information, and then there's some predicted output of the system, which is generated by assuming that if there was no attack or no fault in the system, where the system trajectories would be, right? So you generate the artificial output and you have the actual output, and you take their difference, and you basically try to detect if something is wrong based on this particular residual, right? If this residual is bigger than a particular quantity, then you flag that there's something going wrong with the system and whatnot. Now, a better metric might be to use a sequence of these residuals. I mean, one particular instance of this residual might not give you enough information. So then there's some work in the prior literature also that uses this window of these residual data, which helps better detecting that there's something wrong with the system, and it also accounts for random noises and Gaussian disturbances in the system dynamics also, as it kind of gets averaged over this sequence of data points. Now, one of the issues here is that it still requires a tremendous amount of data for correct fault detection and identification. The idea is that, I mean, how do you generate this expected output? Is, well, you assume that there is no fault, right? And then there is an actual fault, and you take the comparison, but that would only, again, give you that there's something wrong with the system. But for you to be able to identify, well, at what particular instance something wrong started happening and what that something wrong was, you need all possible combinations of data to be gathered and compared against, so that you can actually identify that, oh, this particular actuator became faulty at this particular time instant, right? So that basically requires tremendous amount of data for accurate fault detection and identification. So how do we overcome this issue? Well, one solution that we propose is using a learning-based fault detection and identification, right? And here what we do is essentially we train a neural net on this particular data, right? And then we basically give it all possible inputs during the training, and then expect that, well, with one particular trajectory as its input to it after the training, it would be able to detect as to what particular sensor is, or rather what particular actuator is faulty, and at what particular time instant it became faulty. So that's the idea. So we can use this as as a feature for our neural net. Now there's a better option. Instead of just using this residual data, we can actually use the trajectory data, the input data, and the residual data for training our neural net for fault detection and identification, right? And here, the important thing to note is that U is the sequence of commanded input. Again, we do not have access to the input that actually goes into the system. We only know what input we commanded as the user, or the algorithm that we are running on the system is commanding, but we do not know what actual input goes into the system, right? So it's just the sequence of commanded inputs, the actual trajectory that was taken by the system, and then the residual that was generated. And this residual is just one residual, the actual trajectory and the expected trajectory under the commanded input. So we only have these two trajectory data that is giving us the residual, and when we use this tuple to train our neural net as a fault detector. And the reasoning as to why we want to do this is basically, well, why not, right? I mean, let's see what happens. Anyways, with neural nets, there are no guarantees as to it would perform very well with this particular data or with just with this data, or more data is required and whatnot. So let's see what happens, right? So that's basically the reasoning behind using a neural net-based fault detector. The assumption that we are making is that only one actuator is faulty. So we do not assume that multiple actuators can get faulty or can be attacked at the same time. And to make things simpler, at least for the training part, we assume that the fault model is such that one of the actuator gets completely faulty. So we basically get zero output out of that particular actuator. So we are not considering cyber attacks in this particular scenario, because there we can have a random value of that particular input going into the system, and that basically makes it very, very complicated to train the neural net, because then the space of data that we would need to train our neural net on is essentially infinitely large. So we do not want to do that right now. Right now, we just want to restrict our discussion with the scenario where there's literally no input from a particular actuator, and we want to detect that something is wrong here, and at what particular time instant something wrong started happening, right? And then the data generation, as I mentioned, is essentially a combination of all possible scenarios as to when that fault occur and in what particular actuator the fault occurs, and then we train our neural net. And to keep things simple, we are using an LQR generated input. So if we use a CDF or any other mechanism in a quadratic programming framework to generate these input for data generation for training, it just takes days and days just for the data generation, because I mean, solving a QP for 100,000 points is very slow. And I mean, I'm still not able to figure out how to do it in parallel or a batch processing more efficiently in the Torch framework. But I mean, so right now what we are doing is we are just using an LQR for generating these inputs for the data generation for our trainer. So essentially, this is our training framework. So what we do is we generate different combinations of inputs. So the violet color here marks as to how much length of the input was under attack or under fault. So this first particular set of data was essentially generated with no fault. So your fault detector should also be able to characterize that there is no fault into the system. So we want to minimize false positives. So there is some data which has no fault. There's some data where only the last instant of the input was under fault, and so on and so forth. And then the final set of the data would be when the whole trajectory that we generated was under a faulty actuator. And correspondingly, we generate our system trajectories and then the residual data. Then we collect all this data, and then we train our neural net where the loss function is simply basically the actual theta, which was what the fault vector was, and then the output of this neural net, and then we want to minimize this loss over different iterations. So we keep generating this data over and over again and keep feeding it to neural net, and then finally we stop this when this loss essentially goes to zero. We don't wait for it to go to zero. We wait for it to go to, let's say, a very small number, but essentially that's when we say that, oh, our training is converged, and then we can use it for our fault detection and identification. All right, so if you can use a neural net for this fault detection and identification, we can also use neural net to train our barrier function also, right? So that's what we can do. We can use a learning-based framework for learning CBFs as well as control policies. So now for the pre-fault case, when there is no fault or no attack, we can set up a loss function that looks like this, where essentially we have these three losses. The first two losses are dictating the signs of the barrier function. So it should be positive in the safe state, negative in the unsafe state, and then this is the derivative condition that it should always be positive. This particular expression should always be positive. And so essentially we put these as the losses, and then we train our neural net. So here, our barrier function, the control policy, as well as this class kappa function, which is just a constant, all of them are being trained together by generating data over all of the state space. And similarly, we can also set up a training for our post-fault scenario where we can assume certain kind of faults and attacks, and then we can take the worst case scenario or all convex combinations of those attacks, and then again train our barrier function, our control policy, as well as a class kappa function that we require for our barrier function conditions. And essentially we can learn these things for in offline training and use them for designing our closed loop system finally, along with that fault detector that I presented on the previous slide. Now, one of the things that I noticed after coming here is that, yes, go ahead.
There's a question in the chat from James. He's asking for a clarification on whether you're using an MLP as your neural net architecture.
Can you repeat that?
He's asking.
Sorry, I can jump on. Are you just using like a vanilla densely connected multi-layer perceptron as your architecture?
Yes,
okay,
yes.
okay.
It's a very simple. I mean, so the focus is not on like what kind of neural net would have a very good performance. Right now, we are just using a convolutional neural net with different kind of activation and output activation functions. And what we have noticed is that very simple architectures also work very fine. It's not that complicated to train these barrier functions. For.
Cool.
You said you're using a convolutional neural net? What are you? Is it? Are you passing in like an array of like the past measurements? That's why you're doing some sort of computation on it, or?
So to be fair, I do not know the reasoning as to why we use this framework. What I did was, I mean, there were a lot of neural net frameworks that were already developed by our lab here in the past. So what I'm doing is I'm just borrowing a particular neural net framework where I modify as to what the input of that neural net should be and what the output of that neural net should be. And I don't really care as to what is inside that neural net. I have played around a little bit with the different layer sizes and the different activation functions. And I actually spent a month over that. And then I realized that it actually doesn't matter what you are using. The performance, the most important aspect of this training was essentially how well distributed your training data was. Like, I mean, I actually wanted to explore this as to like which neural net would perform better. Do we need these many layers? Should we increase the number of layers? Should we increase the number of neurons in a particular layer? Should we use different kind of activation functions and whatnot? And then I realized it doesn't matter as long as you have a minimum number of layers and a minimum number of neurons in a particular setting. It doesn't matter what you do. You're just going to increase your computation time and your memory requirement by increasing the number of layers and whatnot, or making it more complicated, but it doesn't help with the prediction accuracy. What helps is you having good enough distributed data on which you train your neural net, and that basically improves your prediction accuracy. So that was what my understanding was.
Cool. Very interesting.
All right. Any other questions? All right. So as I was saying, here we train all the three functions together. We train the barrier function, we train the control policy also, as well as the class kappa function that appears in the derivative condition of a barrier function. But then one thing that I realized is that it's kind of unnecessary to train three things together, and we don't need to train all of them because, first of all, it is a computationally an expensive task to train three neural nets, and it is kind of unnecessary also as I got to know as I played more with that, because what you can do is you can just learn the barrier function and forget about every other thing, and you can still use a quadratic program to find a control policy out of this learned CBF, right? So that's what I think is more efficient. So what we do is, and now I propose that we just set up this kind of a loss function where the only variable here is the barrier function itself. We assume that our inputs are coming from a compact set, so we don't have to worry about how to evaluate this inequality. We can take supremum over the possible inputs, and then we can also put a range for this kappa function, and then we can just find a maximum of our supremum of this particular inequality over these u's and alphas, and then that would still just be a function of one neural net, which is going to be a barrier function. So we can just use these losses to train only the barrier functions for pre and post fault or pre and post attack, and then it reduces the computational effort as well as the time, because it's very difficult to train all three things together, particularly if you notice that there are these terms which basically come in multiplication, right? And when you do multiplication of neural nets, I mean, you don't know what's happening, right? I mean, when you're training these things, you might get into certain local minimas, and then you do not know if it is coming because of these. Anyways, it is non-convex, but I mean, this introduces even more complexity into the training aspect, and then you do not know if your code is wrong, if your data is not well distributed, or if it is because of these highly convoluted products of two neural nets, right? So it's just easier to remove those complications and just train one neural net. And the final result is still same, because at the end of the day, you still use the barrier function in the quadratic program to design a QP online. You don't want to use your offline trained policy at any given point. So it's still the same thing. Right.
Do you impose any Lipschitz continuity requirements on the training?
No.
Okay.
No, we don't do that. So one of the things is the activation functions and other things that we use for the barrier function setup are all differentiable. Like,
Okay.
so our H is differentiable itself, but other than that, we do not assume as to what its Lipschitz constant should be. We do not do that. One thing that we do to kind of like regulate its smoothness is we normalize the data. Well, that's something that we realize is very useful. Is if you normalize the training data, then your barrier functions, first of all, I mean, it's easier to train. The training becomes much more easy, and then the output is also much smoother. So
Cool.
That's what we do. Yeah. All right. So that's what our closed loop looks like. Finally, we have our pre-fault CBF that computes our pre-fault policy, our post-fault CBF that would compute our post-fault policy, and then the neural net-based fault detector that would basically search between those two. And finally, we would input whatever we are going to design to our actual system. Right, and exactly how we compute the policies using these barrier functions. Again, some of you might be already acquainted with these QPs, where essentially we use our quadratic program, learn CBS in this quadratic program to compute the policy. So lambda, if you remember from our earlier slide, was the nominal controller, which uses this pre-fault barrier function that we learned. And similarly, kappa was our post-fault or post-attack policy that we were using that uses this post-fault barrier function. And here we know that we do not use the vulnerable input. We actually design our post-fault policies with respect to the worst case possible vulnerable input. So we only design the secure or the safest components of the input, and we still can guarantee that the system would remain safe and whatnot. All right. So I have some very quick results to show here from the neural net training. So here it basically shows the robustness of our training. So as I said, we only train our neural net for the zero fault case. So technically we train our neural net for this particular case when the faulty actuator has exactly zero input. But then here we notice that even under arbitrarily fault, so in this case, the faulty signal is a sinusoidal signal. In this case, the faulty signal is the maximum possible saturated signal. In this case, it's just a random noise. In all four cases, our safety is maintained at least for a particular duration, and then barrier function is still positive. This is a very interesting comparison. As I mentioned, in most of the literature on fault detection and identification, the X tilde, which was the residual, was primarily used as the feature. I mean, that was not in the neural net setup, so I don't want to call it a feature there, but basically they were just using this parameter for fault detection and activation. And we in our framework proposed that let's use the trajectory, the commanded input, along with this residual. And what we see here is that the accuracy of prediction for different length of trajectories with failed actuator is kind of constant when we use all the data. So here, so essentially during the training, what we did was we took a trajectory length of 100 epochs. And so what it says is that if all of the trajectory components were with the faulty actuator, then the accuracy was at its maximum. But let's say if only one of the components, so if the attack or the fault happens at the last instance before you start predicting, then the accuracy was about 60%, and it increases as you gather more and more, as you gather the data with more components of faulty or attacked components. And on the other hand, with all the data, it's not the case. So irrespective of whether only one component of your trajectory was faulty or the whole trajectory was under faulty data, the accuracy is similar. So that basically kind of shows that this prediction method is better, right? Then there was another thing that we observed, that for the particular case of quadrotor, we don't have to train our neural net for 4 different cases of attacks, right? We can actually exploit the symmetry because, I mean, if let's say the green actuator is faulty, then in case 1, it would be the motor number 2. In case 2, it would be motor number 1. In case 3, it would be motor number 4. And in case 4, it would be motor number 3, right? So we can use this, and because of the symmetry of the quadrotor about z-axis in its system dynamics, what we can do is we can actually just train it on one actuator fault and then use these 4 set of cases in parallel, where we basically do a rotation in our detection function and in our dynamics function to generate 4 set of auxiliary data, and then we can see that the prediction accuracy for the 4 cases is still exactly the same, even when we generate data, or rather train our neural net with just one actuator fault. And finally, this is our closed loop performance. So it is still not as good as I would like it to be, but As you can see, I mean, when the fault occurs, there are certain jumps, and then default accuracy is not that good, but eventually it is still able to keep the system safe at all times. So we are hoping that we get better results. I think this graph shows a little bit better result. I mean, the input, the data was generated randomly, so we get different trajectories. But here you can see that there are certain false negatives, but we are able to detect that there is something wrong more accurately here, but eventually it's unable to detect that something is wrong, but we are still able to keep the system safe in this particular duration. So in the interest of time, I'm going to stop here. I have one more part of the presentation, but I think we are already running over time, and I can take more questions from the audience now.
That was really good. I'm gonna let people ask some questions as well if they're in the chat. There's I think at least 9 people here. But yeah, I'm kind of curious to see a little bit more about like the learning. Like how do you know that the learning is going to be sufficient for what you're doing? Like essentially you've used some sort of learning to construct a control barrier function for your system. How do you know that that is a correct control barrier function, or B, like a usable control barrier function for safety?
So there are two things. I mean, one is that during the training itself, you need to make sure that you are generating enough data, right? So, I mean, essentially going back to this figure, you need to, and this was for the fault detector, but the same thing applies for barrier function training also, right? I mean, one thing that I noticed was if your data is not rich enough, right, you would not get good accuracy in prediction, or like in terms of barrier function, you would not get good performance for your closed loop system using the trained barrier function. So the way we judge that, I mean, we have a good enough function available is that we train it over lots and lots of data, right? So what lots and lots of mean is that for every iteration of this barrier function, let me go back here. Yeah, so here, the end train here for every epoch, we generate, I think, 100,000 data points, and then we repeat this process like about 1,000 times. So eventually, I think we train the neural net over 100 million data points. And so we hope that we have covered whole of state space. And then we divide where we get the data from also, so that we get uniform distribution from everywhere. We need to have enough data from the safe set so that we have one sign of the barrier function there. We have to have enough data from the unsafe set so that we can have the sign requirement there. And then both of these data would be used here also so that we can have the right sign for a derivative condition, right? So it's basically a matter of generating enough data. But then even after we train everything, we do some testing, right, before actually implementing, and we again test our learned functions or randomly generated 100,000 points or so, and then we see what the accuracy is. So just going back to this particular figure, as you can see, it's still not 100% accurate, right? I mean, this was for the fault detection and identification. So that's essentially what I'm waiting for right now. I mean, my training is still running in parallel right now as we are talking, but with whatever results I had, we had about 91 to 92% accuracy in detecting correctly which particular actuator is faulty at what particular time instead. So,
and so what's the impact of this prediction accuracy not being 100%? Like,
so the impact is that to be able to generate this figure that does not crash, you need to run like 10, 12 simulations, and then you get one of those simulations, right? So that's one of the problems with neural nets, that, I mean, this is a statistical result, right? I mean, 95% of time, you would get right performance, right? But then if you pick one of those cases, you actually do not get good performance, right? Because again, out of 100 cases, certain number of cases would be good, but then one particular case might not be very good. So that's one of the implications. And that's something that I've still yet to explore, because that's one of the problems that I've always had with neural net papers, that all the guarantees, all the well, I don't want to call it guarantee. There's no guarantee, but all the performance metrics are always with respect to these accuracy measures, right? And which is again out of 100,000 trials, 95% time we were correct. So that's good. That's very good. 95% is seemingly a very good accuracy, but then that particular one instant out of those 0.05 or 0.5 or 5% where you are not good, if that basically is your trial during the actual run, what would happen? System would fail, right? So no one talks about that. So I mean, I'm not saying that I would be able to achieve like 100% accuracy at any given point, but like how do we bridge the gap when we are not confident that our trained neural nets are good enough, but at the same time we do not want our system to basically fail because of this is something that we are still exploring. I think at the end of the day, we still need to use some sort of fail-safe measures in our implementation to basically do something about it when the system fails.
I can imagine there has to be some sort of like robustness again, at least some epsilon of accuracy not being 100%. So you'd have to like at the control barrier function side, when you're like writing out your actual final controller, you have to assume that you would have to like, I don't know how exactly you do this because it's not a robustness condition, but you have to be somehow robust to I have mispredicted that my system is safe or is
that's true. That's true. Yeah. I mean, so more recently, what people have started doing, I mean, we were submitting, not we, but some of the people in my lab were submitting a paper just last week. I think they were also talking about formal verification of neural nets, right? I mean, there's a lot of discussion about it as to how do you verify whether a neural net is correct. And the idea is that you can use formal methods for it, where you can use some sort of what is it called? The reachability analysis of the neural nets and other different ideas to verify whether your neural net is correct. And some people have started using it in the training also. So you use some SMT solver or other formal method tools where basically you train your neural net, then you basically pass that neural net into an SMT solver, and then it would either certify that your neural net is correct, or it would give you a counter example, which you would again account for in your next training epoch. And so it could be an iterative process, but then again, I don't know. I mean, so again, what people say is that, I mean, as n tends to infinity for this particular process, you would have an accurate representation, but I mean, there's nothing called as n tends to infinity, right? I mean, you can only train on finite number of data for finite number of iterations. So this gap is still exists, and I do not know how to bridge it. Yeah.
Yeah, I was looking into some pack-based bounds recently. Like there are some like it is asymptotic, but there are some like guarantees that if you had enough samples, and those are very conservative sampling estimates, but at least they give you like some upper bound on n, which is if you have n data points, you'll have maximum epsilon error.
Right. There's a lot of work on this from the UPenn group, right? I'm not sure if you're talking about the same thing, but I think I'm forgetting the name. It was just a collaborator, Nikolai Matny. He has a lot of work on this as to how much data you need to be able to learn properly. And he has these results for linear systems. He starts with linear systems first, but then I think he has these closed form expressions that if you have a linear system of this particular dimension with this particular controllability metric or uncontrollability and whatnot, then you need data which is polynomial or exponential or whatnot in the system dimension. In this, so he has certainly theoretical results on that, but
this is the particular archive paper that I was looking at. It's like a gentle introduction or like a tutorial paper on pack bounds, but it's kind of interesting that they have like an actual number. It's not just like it grows with n squared, right? Like the epsilon error is going to like tend to log n. It's like this is the number of samples you need to correct it.
Okay. Yeah, I haven't seen this one, but all right.
Yeah, it's interesting.
Thanks. Okay. Any other questions?
Yeah, a question from here. I'm just curious, Kunal, have you looked into adversarial perturbations to the machine learning model itself as possibly generating more training data?
Yeah, I haven't done it. I haven't looked into it, but yeah, I know that a lot of people do it, right? Adversarial neural net training and using adversarial neural nets and whatnot. So I haven't done it personally. I mean, I'm still very, very new to the field. I think people would know me, know that I still don't have any paper in neural nets. This is the first time I'm working on it. So right now, my objective is just to see how neural nets really work, right? And I'm open to using different kind of ideas. I started looking into GNNs for multi-agent problems, particularly as to how effective they are to exploiting graph symmetries when we talk about, particularly when we talk about unidirectional connections between multi-agent systems and whatnot. And but yeah, to answer your question, no, I haven't explored that.
Oh, no worries. Yeah, I was just curious, and I'm pretty new to neural networks as well, but no, it's because that could be one direction to explore of, because they
Right.
have methods where you can, basically use an optimization problem to find, a perturbation to current data points that takes them most rapidly towards being like infeasible or a different answer. So that could be at least another way you could augment your training data and see where the weak points are.
That's true. That's true. Yeah, I think that could be a very good way of kind of like, again, not certifying. I don't want to use that word, but basically assessing where your neural net training is lacking.
Mhm.
Yeah, good point.
Nice.
Any other comments, questions?
I have a question about sort of the theoretical maximum performance in your
Yeah.
in your training scenario. So it seems like, at least my understanding, there's no stochasticity in any of this. So theoretically, if you have a perfect model of what's actually happening in the simulator, your a neural net with infinite capacity should be able to learn 100% accuracy. I'm kind of
That's true.
curious if you thought about how this would degrade, if you have highly uncertain dynamics, external disturbances that aren't modelable, that are random, you may not be able to tell whether an actuator is out or whether there's
Yeah,
a lot of wind, for example. So I'm curious.
that's a very good point. That's a very good point. So that's something that I was always curious about, as to how do you distinguish between trajectory perturbations coming from disturbances or actuator faults and actuator attacks, and that has always been one of the biggest questions. In terms of theory, I still don't have any answers. I mean, I've read several papers, I've written a couple of papers, and everywhere we assume that, oh, I mean, there are no disturbances right now because we can't deal with both of them together. In terms of performance, what I've noted was, and I don't have a figure to show right now, but what we did was, at time of training, we didn't use any disturbances, but at time of basically assessing the accuracy, we introduced random perturbation in our system dynamics. And what we noticed was the accuracy was actually very, very similar. There was not much degradation in the performance and during the testing time of this neural net. So that's one of the things that I'm very, very, you can say, impressed with neural net performance, as I presented in one of the figures, that we trained it for zero input case, right? Where that the actuator is completely faulty, that there is there's no input from that actuator, and then we assessed its performance against different kind of faults, where we had sinusoidal input coming from that faulty actuator, or a maximum input, or a completely random noise coming from that actuator, and the system is still robust, both in terms of detection and keeping the system safe. Another thing was, as I mentioned early on, very, very briefly, that we generated all our data using LQR, because it's very fast to generate an LQR-based control input, right? I mean, it's just a constant multiplication. But then at the time of testing, we are actually using our learned CBF for generating these trajectories, and we want to detect something is wrong with respect to our CBF trajectory, right? And again, the fault prediction and everything was exactly the same. I guess I can again share the screen here, and you can see that these plots, there are 4 plots here, the 4 lines there. 2 of them are for LQR trajectories and 2 of them for CBF-based trajectories. And as you can see, the prediction accuracies are almost similar to both of them. While the training was performed on LQR, the testing was done on CBF-based input and CBF-based trajectories, and it's still the same. So in essence, what I've noted, again, you cannot prove it, but what I've noted is that somehow neural nets are very, very robust to generalization. I mean, we still cannot prove it, but the performance basically shows that they are very robust to different kind of input generalization. Again, as it was shown in this figure, that we train it for this, but even for this input or for the sinusoidal input, you can see that it responds very well, particularly the barrier function here. I mean, as you can see that the output of other motor, you can see that it is responding to the input that we are giving to this faulty motor, while it was never trained to do so, right? So we trained this faulty barrier function just for this particular input, and here you can see it responds by switching off another motor so that it can maintain its orientation properly and whatnot, but like it's able to respond to this random noises also, which basically kind of illustrates somehow it is very robust. I don't know how. I don't have answer to why, but it is. So yeah.
Here's another question, Kunal. Have you ever so I'm curious about the comparison of this approach versus like adaptive control. I know recent adaptive control methods have started trying to throw neural networks into the mix, to adapt to that. So what would you say the differences between this control barrier function approach and adaptive control are?
So not much, I would say. So essentially, if you go back, I guess, where was this? There was this particular slide where I was presenting the basic idea. If you think about this, so here I'm just saying that my U is modified, particularly for the fault detection part, right? So here I'm saying that there's this theta parameter that affects my U, and this theta parameter is unknown, and it's constant also. It's not even time varying. At some particular point, it goes to 0, and then it stays 0. I mean, one of the components and everything else is 1. So the initial thought that came into my mind was also to pose it as an adaptive control problem, right? So what I would do is I would want to learn the theta dynamics, and then I would update the theta in real time. I would have a theta head, and I would design everything with respect to that theta head. And I mean, I would hope to get better results. So, which was all fine. And then I thought that, I mean, there is some work on that, but for you to be able to guarantee that this theta dynamics converge to actual theta and that your system also has a certain performance, you need to, again, make a lot of assumption that you are getting rich enough data from your system trajectory. So you cannot always guarantee that your theta would converge. You need persistence of excitation and whatnot. So then to remove all those complications, what you can do is, instead of using a dynamic to predict what theta is, you can actually just learn this theta, again, just generating that persistent trajectories for that training, and then store everything offline, train it, and then have a neural net, which is basically replicating that theta head dot dynamics, where you don't need any persistence of excitation in real time right now. I mean, almost always you would not need that. I mean, there would be certain cases where you would not be able to distinguish as to what's happening with the system, but I mean, you can hope that you would still get very good performance, but you would not be able to prove that what you are getting is correct. I mean, in adaptive control framework, you would have theoretical proofs, but then it also comes with the caveat that you need those certain technical assumptions and setup to be able to show that this would work. But here you don't need those assumptions, and then you don't have the proofs. So the idea came from adaptive control framework, but then I thought, let's explore what happens in the neural net framework here.
Yeah, I honestly, it'd be interesting. I don't think I've ever seen a side-by-side comparison of the adaptive control approach with this CBF approach, because I think
that's a good idea.
Because adaptive, they do a very similar thing where you can sense the disturbance and adapt to it. Like if you lose a prop or something. So I think that would be a very interesting comparison to say side by side. I mean, the approaches are obviously different, but the benefits, what's the gap in the adaptive control side? What's the gap in the CBF side? And honestly, that could be a very good opportunity to say, when we put these two together, what happens? I mean, because it'd be interesting to see if both of them combined could make up for this, for the weaknesses of each other and combine the strengths into something interesting.
Yeah.
Because yeah, with adaptive control, once you throw a neural network as the as the basis function or whatever, then you kind of lose guarantees to some extent as well. But it's if you're, like you said, if you're testing with enough data, it'd be interesting to see if the performance. Yeah,
That's
if you get pretty good
That's
performance
true.
anyways.
Yeah.
That's a really cool idea. Yeah.
Yeah, there are a lot of things that I want to do with this neural net framework. Like, just comparing it with different kind of theoretical frameworks, just comparing different sort of neural nets, their performances and whatnot. I have a bunch of ideas here. It's just that the time is limited. And resources are the only constraint here, right? If I was a PI right now, and if I had like a bunch of students working for me, I would basically make them do this.
Apply that grad student descent.
Yes.
Just curious, what a framework are you using for your neural networks? Is it the MATLAB deep learning, or are you using like PyTorch?
PyTorch. Everything
Okay.
is based in PyTorch. Yeah.
Okay.
All of our code is available online. Let me pull it up. So, so this is still under development. I don't recommend people using it, but if you just want to see, you can see the code here. I hope it is public. I don't remember now. Yeah, I think it should be public.
Yeah, I can open it.
And then the broader framework that I'm using, I can send that one to you because that is published work, right? So that's from our lab, and I'm using neural nets directly from there. I think that would be easier. Yeah. So this one.
Cool.
Near CLBF. So this is very, very good one. I don't know which one is the main here. There are a lot of threads, but
You're doing some fixed time optimizers as well?
oh, that code is there. That was not there. Yeah, that's a problem. I didn't know. I was trying to train a fixed time CLF also. Again, I just wanted to try everything, right? As to
Sure.
how these things work, right? So this code is from where I borrowed my neural CLBF. So broadly, this is called as neural CLBF framework, right? So Charles Dawson, our PhD student in our lab, he developed this, and he has a couple of papers. But the idea is that any notion of function, either Lyapunov or barrier or a Lyapunov barrier function, if you want to train, he has written a general toolbox for that. Not a toolbox, but general framework for that, where you can put in your dynamics, your constraints, your safe set, your goal set, and whatnot, and then it would basically train everything for you, right? So he has some examples on it, but you can also use the package for your own training. So that's basically
really cool.
what I use for setting up the neural nets.
That's really, really cool. So it's like point-wise constraints that you're asking it to satisfy across the whole state space, right?
Right. With
So you don't
certain
have to-
epsilon, as, let's say, your, what would you call it? Basically,
like a margin.
yeah, some sort of a margin to account for the distances between your sampling points. But yeah,
Okay.
so
So
the
it's like
idea
some
is that, yeah.
you've got some sort of like epsilon net that you're trying to solve over?
Yeah, so here, essentially, in some sense, yes, that epsilon net solvable. Essentially you want that between, we are not sampling with respect to this epsilon, but I think the broad idea still is that this epsilon is large enough and your sampling distance is small enough, then you would essentially cover the whole state.
I see. So if you had some sort of Lipschitz constant, then you would be able to say this epsilon guarantees
Right,
that the boundaries are correct.
Yeah, yeah. So that can be imposed. We don't do it, but yes, if your epsilon is essentially your Lipschitz constant time distance between sampling
Mhm.
points, or the minimum distance between maximum of minimum distance between sampling points, then that would have the theoretical guarantee. So that was the third part of my talk, but I didn't have time for it. So if people are interested, they can read my paper on sampling based computation. I can actually put a link here. Let me try to do that.
Cool. Yeah, I'll make these links available for people that watch the recording as well.
Yeah, let me see if I can. Yeah. So that was essentially what I was doing last before I joined MIT, which was basically trying to explore like how sampling these methods can be used for these computations. So I mean, how to assess whether this barrier function is correct or not, and something like that, right? So I guess kind of very, very briefly, if I were to like go ahead, yeah, the idea was this, right? We want to assess whether this inequality holds at each point. What we can do is like we can sample with certain relaxation, not relaxation, rather it would be a contraction parameter, and then this contraction parameter would be a function of like how closely we sample and what the Lipschitz constant of this function is, and then this satisfaction of this inequality at these sample points would imply satisfaction at each point on the boundary, right? And then I think, yeah, that's how do we efficiently sample, and then this gamma turns out to be exactly like the Lipschitz constant times the distance parameter between the sampling points, and then, yeah. So that was the idea.
You're assuming you can sample on the surface.
We are only sampling on the surface, yeah.
Okay. Cool.
Yeah. So one thing that I was focusing on this work is like, you don't want to learn CBF everywhere, right? So the idea was at the end of the day, what you're concerned about is the CBF inequality
Is in the margin around
on the boundary, right? Whenever we say that a function is CBF, I mean, there are different notions and different definitions, but like when we subscribe to this particular definition, which is this, that this inequality should hold on the boundary, right? I mean, something can happen inside, something can happen outside, we don't care. As long as this inequality holds on the boundary, we can guarantee that system is safe, right?
Yeah.
So then we only need to assess that this inequality holds on the boundary. So we only want to sample on the boundary and check if this inequality holds on the boundary for a particular function. We don't care what happens inside or outside. So that's why it's more efficient also, because the boundary is just a zero measure set, right? And it's very, very efficient to sample it and check those n number of points which are not going to be inputted because it's just a zero measure set.
No, but generating a random sample on some boundary, like even if it's a level set curve, it's not. I mean, that's the computationally tricky part as well, right?
So it's not random. So we don't do random sampling. Random sampling would be very inefficient. So we actually propose algorithms as to how do you do sampling. So we say that, I mean, assuming that the sets are compact and they are smooth enough, they are diffeomorphic or at least homeomorphic to spheres, what you can do is there are algorithms, there are triangulation algorithms available online that you can use, and they're very efficient. They do sampling in like 0.1 second, they generate 100,000 samples.
Really?
Yeah, triangulation is very, very efficient. And for higher dimension also. So this, I mean, I can only show a figure in 3D, but like you can imagine in 4D, 5D, ND, you can have simplex, right? And then you can still do the sampling. And then we extended our own algorithms. I don't think I have it here. Let me see if I have my algorithm. I might not have, yeah. But the idea was that, I mean, again, you can exploit symmetry, and what you can do is starting from one dimension, you can sample 2D. Using those sampling in 2D, you can sample 3D, and then you can from n minus d, you can sample nd. And that we showed that even simplex, finally, like it takes like 0.1 or 0.2 seconds for everything. And my algorithm, it took like order of magnitude less, like 3 orders of magnitude. It took like 0.001 second for sampling 10-dimensional sphere.
So,
which is
okay,
very
so let me
efficient.
see if I understood this right. Let's say we were trying to stabilize a quadrator. We're trying to find the Lyapunov function in a controller.
So this
that
is not for
stabilizes-
Lyapunov function. This is for safety. This is for barrier function. For Lyapunov function, you have to sample the whole
right.
state
Okay.
space. Yeah. So this is only for safety. For barrier for Lyapunov function, what we did was something similar, where essentially what you do is you I think that's still work in progress. I'm working on that paper, but the idea is like, I mean, you sample this and then you go inside and then you sample another boundary, then you sample another, and then you would have. So I have a paper on that, but we are yet to submit. But the idea is like you can find out the distances, if you will, between different surfaces and distances between points on a particular surface, and then that would dictate the number of sampling points. And then again, we showed that it's actually going to be linear in the system dimension. And then with those many points, you can sample the whole state, not the whole state space, but any compact domains in that state space. And you would be able to assess whether an inequality holds everywhere in this compact domain using those finite number of sampling points. And again, how do you do it? We have a very, very efficient algorithm to do that.
Very cool. Okay.
Yeah.
Yeah, I'm definitely interested to learn more about this because I've been trying to think about how we can take, you know, let's say we've got a quadrotor that's trying to fly around some space. That means we have some sort of safe convex polytope that you have to stay within. Let's say it's centered about the current quadrotor position. That means the only real variable is like the velocity of the quadrotor. So now I want to certify what set of velocities or what sort of forces on this quadrotor are going to keep it safe. So I want to like grow this like grow some sort of like barrier function on the inside of this polytope, and then certify that I can be safe against multiple constraints at once.
Okay.
So I've been trying to think about how I would train some like a neural net or some sort of barrier function or what that, you know, the learning process has to be so that I can certify a safe control policy. But I've been struggling with the sampling problem where you need to sample on a quadrotor, which is, you know, this like 20-dimensional state system or 12-dimensional at the very least.
Right. Yeah.
9 if you
So
like,
if you are interested, we can talk. I mean, I have some preliminary work already published on this in conferences, and we are working on the final. We are just wrapping up our journal paper on it, which we are hoping
cool.
to
Yeah,
submit
definitely interested to learn more about this.
Okay.
We'll set up a time and talk about it more.
Sure. Sounds good.
Yeah.
All right. Great conversation.
Yeah, thank you so much.
Yeah.
I really enjoyed this.
Absolutely. Yeah, it was my pleasure. Thank you so much for having me.
Yeah. And if you're ever around, please come visit.
Absolutely. Yeah.
All right. Thanks, guys. Thanks everyone for
Anyways.
attending. See you.
Yep. This is great.